So in this lesson, we're going to be taking a look at what's called the remainder theorem, and this will help us to use synthetic division to actually evaluate polynomials in what I think is a simpler and faster way. Alright, so don't write any of this down. If you pull up the notes from my website, obviously you already have this, but if you do notes paper and pencil, you don't need to write all of this down. I'm just going to kind of explain where the remainder theorem comes from so that you understand why it works and why we're able to apply it in the way that we do. Alright, so first, think that you have a polynomial f of x. So we saw synthetic division yesterday. This f of x is what we are dividing into by x minus c. And again, the only way that we can use synthetic division is if it is a binomial term where the lead coefficient of the x is 1. So this is what we're dividing by, and this is some function that we're dividing into. When we divide, we could rewrite the division as a product of what we divided by and the result. So to simplify this so that this piece makes a little bit more sense, think about if you take 12 divided by 4 equals 3. So I am going to jot that down for you visual people. Another way to write that is to say that what we divided into, so again, this f of x, this is what we divided into, we could rewrite that as what we divided by times the result. So rewriting this as a statement of what I divided into equals what I divided by times the result. So that's what this is saying right here. This is what we divided by. We can multiply it by the quotient or the result of the division. So that's this q of x piece. Plus there might be a remainder. In my simple example here, we didn't have a remainder, but if we did, we would add that onto the end. So this is the remainder function. But remember, the remainder is a constant. Every time we did our synthetic division, if we had a remainder, it was a constant. There was no x part to it. So instead of calling it a function of x, we're just going to call it r, some number that's the remainder. The next piece that we're going to look at is where the remainder theorem comes from and where the applications are important. So let's see what happens if you have x equal to c. So if we replace our x with a c, this becomes c minus c, which is 0. So that makes this product equal to 0, and we're left with the remainder. Look over here. This is evaluating the function at c, replacing that x with a c. So if we want to evaluate a function, we can use synthetic division, and the remainder will be equal to the value of the function evaluated at that c value or some number. So that's exactly what this remainder theorem says. When you divide a polynomial f of x by x minus c, some linear binomial with a lead coefficient of 1, the remainder will be equal to evaluating the function at c. Alright, this next piece says, what if you calculated f of c and it was 0? That means the remainder is 0, and x minus c is a factor of the polynomial. So if there's a remainder, x minus c does not go into the function evenly, so it is not a factor. If there is no remainder, it is a factor. So again, going back to my example up here, 12 divided by 4, I want to apply this to something that I know you understand. 12 divided by 4 is 3. There was no remainder, so that means 4 is a factor of 3. If I tried to divide 12 by 5, I would get 2 with the remainder of 2. That means 5 is not a factor of 12, something you already know. Alright, what is the remainder for this function once it's divided by this? So we can use our synthetic division. This is a linear binomial with a lead coefficient of 1. So we're going to set up our synthetic division. I'm going to grab our lead coefficients, or all of our coefficients, I should say. The lead coefficient is 1. And we're not missing any terms, so I don't have to fill in any zeros. And remember, when we divide by synthetic division, we have to pull that out of the asylum. What we're doing is we're actually using the 0 of the binomial. Drop the 1 down, multiply by negative 2, add, multiply by negative 2, add, multiply by negative 2, and we get a 0 for the remainder. So the first question, What is the remainder of the division? Well, the remainder equals 0. And what does it mean? Well, it actually means two things. What it means is if I call, let's see if I can point here, if I call this function f of x, it means f of negative 2 equals 0, and it also means that x plus 2 is a factor of f of x. All right, let's take a look at one more application of the remainder theorem before we go on to our next video. This one is asking us to evaluate the function at g of 3. Now notice this time I did not give you a binomial, I gave you the actual value. So when we set up our synthetic division, we are going to use 3, not negative 3. So starting with our coefficients, and this time we're missing a term. We don't have an x cubed term, so I'm going to put 0 for my x cubed. Negative 15x squared minus 10x plus 5. Dividing by 3, we're going to drop our 2, multiply by 3, add, multiply by 3, add, multiply by 3, add, multiply by 3, and add. Alright, so g of 3 equals the remainder. Sorry about the writing. So if we substituted 3 into the function and performed order of operations, we would get a value of 2. So synthetic division is just another way to evaluate a function for a given value.